Okay, hello math people. So this morning sadly, I forgot to record the lecture that I gave. So now I'm doing a recording and I'm going to do the whole thing over again. So I just ate a cookie for emotional support and now I'm just going to go through this whole thing over again. So basically, I guess I'm just going to go through the whole thing, except I won't really have any pauses for questions from students, but I'll try to work in the answers to any of the questions that were asked during the actual lecture. So this week we're going to start in talking about trigonometry, which for some students, they find trigonometry intimidating because it's one of those things that you've just heard your elementary school teachers and your middle school teachers and your high school teachers say oh, when you go to college you'll study trigonometry, and it's just this far off away thing that seems scary. And part of that, I think, is perpetuated by the fact that a lot of instructors, in my opinion, teach trigonometry in a very unintuitive way. So to remedy that, I'm going to try my best to communicate trigonometry to you in a way that is intuitive and understandable, and hopefully you find it to be reasonable as well. So this week we're going to talk mainly about angles, the unit circle, and some trigonometric functions. And today we're really just mainly going to focus on angles, and tomorrow we'll work more on unit circles and sine and cosine and tangent and that stuff. Okay, so before we can really talk about trig, we need to understand what an angle actually is. Okay, so what is it? Well, an angle is a measurement, okay, which is going to express the difference in direction between two rays. Okay, so we start at the same point. One ray goes out in one direction and one ray goes out in another direction. And we want to somehow quantify the fact that these are going in these two different directions, and what is the difference between those two directions and, say, a third direction or a fourth direction. We want to say, what is the relationship between these directions of these rays? Okay, and basically, we have kind of two main ways of doing that, using either degrees or radians. But the most important thing is that our definition should be consistent. So however we quantify this angle, okay, we should, for example, have that the angle which looks like this angle should have double the measure of the previous angle, right? If we consider going to this ray 3 here, we should be consistent and say that angles which look like they're about double the difference should have double the measure. Okay, and how much the original measure is less important. And there's two kind of main schools of thought for how to quantify this distance, and we'll talk about both of them today. But before we talk about those, let's just kind of get a little bit of our terminology on track. So we call this first ray, okay, from which we measure the angle. We call, oops, that's not a highlighter. We call this ray number 1, we call it the initial side, okay? And we call the ending ray the terminal side. And the measurement of the angle is as we move from the initial side to the terminal side, okay? And which one is the terminal side and which one is the initial side does matter, okay? Because we have a notion of what it means for an angle to be positive and for an angle to be negative. Okay, so we call any angle positive if it's given by counterclockwise rotation. Okay, meaning if we think about the hands of a clock, they go around in this direction. This is clockwise. And if we think about the other direction, we call that counterclockwise or anti-clockwise. Okay, so clockwise is like turning our steering wheel to turn to the right, and counterclockwise is like turning our steering wheel to turn to the left. Okay, so if we have an angle which is given by a clockwise rotation, such as this angle here is given by a clockwise rotation, we take this ray here and we rotate it, counterclockwise to get our second terminal side, then we call that a positive angle. And a negative angle is one given by a clockwise rotation, for example, something which looks like this. So in this case, our initial side, it's not my highlighter either, our initial side, okay, is up here, and then we rotate it clockwise in order to get to the terminal side. So we would call this angle a negative angle. Okay. Okay, so one more thing before we get on to degrees and radians, we want to talk about what it means for angles to be coterminal. Okay, so coterminal really just means same ending. Okay, coterminal means same ending. And angles are going to be coterminal if they share the same terminal side. Okay, so for example, here are two angles. The first angle here is this angle theta, which is given by taking our initial side and rotating it counterclockwise to get to our terminal side. And we say that that angle is coterminal to the angle beta, which is given by starting at the same initial side, but rather than going clockwise, we go counterclockwise. Rather than going counterclockwise, we go clockwise. And we wind up at the same terminal side. Okay, so the property of these coterminal angles is that they have the same terminal side. And I wrote down some of these common letters that we use to describe angles, okay? So I don't want anybody to get confused by this Greek business. We just have this letter here is the letter theta. It looks like this, or sometimes we draw it with a little squiggly in the middle. That's just a Greek letter, and it's just like a variable. Then we've got alpha, which looks a little bit like a fish. Beta just kind of looks like a bee with this kind of elongated tail here. And I don't know, we probably won't really use gamma, but gamma looks like an upside down fish. Okay, so those are some of the letters I'll be using to talk about angles. Okay, so in this case, we have two coterminal angles, one of which is a positive angle. The theta angle is positive, and beta here is a negative angle. Okay, so it's possible for positive and negative angles to be coterminal as well. All right, so how do we actually assign a quantity to describe the measure of an angle? Okay, how do we actually describe this quantity? So we have, first of all, degrees. Okay, and the way degrees work is we assign to an angle, okay, 1 degree is the measure that we assign to an angle which represents 1/360th of a full revolution. So if you've ever heard of somebody doing a 360, like on a, I don't know, at the X Games or something, okay, what they mean is they turn all the way around, which is kind of like you say, if I'm facing one direction, right? If I'm facing this direction and I have a ray which comes out of my chest, if I do a 360, then the top-down view would be that this ray has gone all the way around. So this is top-down. So if this ray here is coming out of my chest and I do a 360, that means that I've turned all the way around and I'm looking back in the same direction in which I was originally facing. So here's an angle which looks like something around 1 degree. It's really kind of small. And if we basically, did this 360 times, then we would eventually get all the way around. Okay, that's the point. Is that we do this 360 times, then we would be facing the original direction. So that's how we use degrees, okay? And there's a couple important degree measures which we'll now talk about. So first of all, a right angle has measured 90 degrees, okay? And this is an important angle because it has all sorts of nice properties. First of all, if we do 4 of them, then we get a full circle, or a full 360, because, well, 90 times 4 is equal to 360. Okay, and second of all, they're important because when we have a 90-degree angle, okay, if we have a 90-degree angle, then we draw this triangle in here. This triangle will obey the Pythagorean theorem. Pythagorean theorem. Okay, in other words, if we have a and b, then this side will be the square root of a squared plus b squared. Okay, so this, we can find the hypotenuse using the Pythagorean theorem. So right angles are very special. And because they're so special, we give them a special symbol, basically, which we put in the angle here. So usually we would put an angle, it looks something like this. We do this little curve. Okay, but if it's a right angle, instead of a curve, we use this little box. Okay, and the box means that the angle is 90 degrees. Okay, so that is what a right angle is. We'll talk more about right angles later on. Okay, so then we've got acute angles, all right? So any angle that is less than 90 degrees is going to be considered acute. Okay, so something like this picture here, or this dude from Family Guy here is kind of shaped in an acute angle. Or if we look at this animation here, we can see that all of these red angles of this red thing going up to 90 degrees, but less than 90 degrees, we call those angles acute. Okay? And we've got another word for describing when an angle is not acute. We call it obtuse. Okay, and an obtuse angle is just a measure of an angle. It's just what we call an angle whose measure is between 90 degrees and 180 degrees. You can sort of, I guess, think of an angle which is larger than 180 degrees as obtuse as well, but it kind of loses all meaning at that point. Okay, so here's a picture of this guy, and he's kind of lying down in an obtuse angle. All right, so we can also have angles of more than 360 degrees, okay? This is no problem. We can still do this, okay? And the only thing we have to consider is that basically we just go, if our angle is 405 degrees, we just go 360 degrees plus an additional 45 degrees. Okay, we go 45 degrees past 360 degrees. Okay, so we go 360, we start in the middle and we get out all the way around to where we started before. And then we just go 45 more to get to where we want to be. Okay, so that's how angles of more than 360 degrees work. And likewise, we could do a negative angle of 405 degrees. It'll look a little bit different, okay, because of course when we do a negative angle, we're going to move in a clockwise direction. Okay, so we start here, we go all the way around to 360, and we're back facing where we were originally facing, and then we go another 45 degrees after that, and wind up on this terminal side. So here's the terminal side. And this is our initial side. This is our initial side. Okay. So angles of more than 360 degrees are no problem. Okay, so how do we actually draw these angles? Well, typically, if I'm given an angle in terms of its degrees, I'm just going to understand it as being either a multiple or a fraction of a 90-degree angle. Okay, so I just consider these. I know what a right angle looks like. So if I want to draw what 45 degrees looks like, I just consider 45 as half of 90, and then I just draw a 90-degree angle like I've drawn here in this yellow. And then I consider, well, what would an angle look like if it had half of that measure? So I just divide it in two like this, and then that's how I would draw a 45-degree angle. And likewise, I can do that sort of thing for like 30 degrees is 1/3 of a 90-degree triangle or angle, and then 60 degrees is like 2/3 of a 90-degree angle. And we can also do things which are more than 90 degrees by considering, well, something like 270 degrees. If I do 270 divided by 90, I would get 3, which is what's telling me that I get basically 3 right angles all lined up next to one another. So the 270 degrees will be all the way through these 3 right angles. Okay, so that's how I can draw 270 degrees. Okay, so hopefully we're getting a pretty good grasp of these degrees at this point. So 360 is all the way around, and then any fraction thereof is going to represent a fraction of a full revolution. Okay, so now we're going to talk about radians. Okay, and I don't want anybody to be confused by radians because essentially a radian is just a different unit of measurement for an angle. Okay, so just like how people in the rest of the world measure things using meters and centimeters or degrees Celsius instead of how we would measure things in the United States using the imperial system, which is like, you know, yards and feet and degrees Fahrenheit and these sorts of things. Okay, so just like how we have those different units of measurement and we can convert between those different units of measurement for things like length and temperature, we have different units of measurement for angles, okay, and their degrees and radians. Okay, so radians is just a different way of looking at things, and instead of saying that 360 degrees is 1 full revolution, the new perspective we take, okay, is that 2 pi radians is 1 revolution. Okay, so this is just a different way of looking at things, and in a lot of ways it's a better way of looking at things. But degrees is just something that we've had around for a really long time, and nobody really knows where it came from. But it's here, and it's how a lot of people just understand, turns. Just like in terms of common speech, right? Like if I saw somebody, at the X Games do some kind of spin move, I'd probably use degrees to describe their spin. I'd say they did like a 720 or something like that, because they did a 4 pi radian spin. Just doesn't really roll off the tongue in the same way. So we have these two different things, and really degrees is good for just like speaking, and radians is good for math. So most of the time when we're talking about doing math, we're going to use radians just because it makes all the computations very easy. Okay, so we have the following relationship. Since 2 pi radians is going to be 1 full spin, and we know that 360 degrees is 1 full spin, then we can use this equation here, which says that 2 pi radians is equal to 360 degrees, to figure out how to convert between the two. Okay, so if we just solve each side for 1 degree or for 1 radian, okay, then we find out that 1 radian is approximately 57.29 degrees. Okay, and we get that 1 degree is something like 0.01 dot 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 radians. Okay, so we can just get that by dividing each side by either 2 pi or dividing each side by 360. Okay, but I don't want you guys to memorize this information. It's pretty much useless. It's just to give you an idea that 1 radian is a much larger angle than 1 degree. Okay, that's all that I'm trying to really say here. And in practice, we would never use these numbers to like convert between forms. We'll use a much smarter way, which I'll talk about in a minute. But first, let me explain how radians actually make more sense than degrees. Because the way we measured degrees was basically just arbitrary. We just pulled this number 360 out of thin air, and we said, okay, 360 of them is a full revolution. But I'm going to explain now why 2 pi is a really great number to express a full revolution of an angle. Okay, and the way we think about it is as follows. If we think about a unit circle, okay, so a circle with radius 1, we call that a unit circle. And the nice thing about a unit circle is its radius here is 1. Okay, so it's a diameter of 2. Okay, and we can think about the circumference of a circle like this. The circumference of a circle is equal to 2 pi r, where r is the radius. So for our case, if we have c equals 2 pi times 1, we would get just 2 pi is the radius, the circumference of this circle. And now the kind of clever way that we define a radian is we say that 1 radian is the angle measure which produces an arc length of 1 on the unit circle. So if I draw in 1 radian, I don't know, maybe it looks something like this. So we call this angle 1 radian. Then the amazing thing is that this length of my pizza crust here, basically, will be 1 unit. Okay, so this is how we define radians, and it's smart in the sense that if we consider 2 pi radians, then the arc length would be the entire circumference of this circle, which we know to be 2 pi. So 2 pi radians gives us an arc length of 2 pi. 1 radian gives us an arc length of 1. Okay, so this is the way that radians were defined, and it's sort of convenient in that way. Okay, so how do we actually draw radians? Okay, well, I'm just going to consider these different values of these radians here as, again, portions of a full revolution. I know that 1 radian, I know that 2 pi radians is a full revolution. So if I do 1 divided by 2 pi, 1 radian over 2 pi radians, then I know that this is going to be like 1 over 6.28 dot 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 is approximately 1/6 of a full revolution. So I would draw a circle, and then I would put on my initial side, and I would say, well, I want to go 1/6 of the way all the way around. I know that here would be 1/2 of the way all the way around, here would be 1/4 of the way all around, so I want to do even less than that. 1 radian should be somewhere around here. Okay, so here's 1 radian. Okay, so you can do that, or if you really want, you can change it to degrees, and if you like degrees more, then that's perfectly fine. We'll talk a little bit about how to switch between those two forms in a minute. So how about pi radians? Well, I can think of this again as a portion of a full revolution. I know pi is what we're doing. I know 2 pi is 1 full revolution. So I can cancel these pi's, and I would get that this is 1/2 of a full revolution. So what does that look like? Well, it just looks like halfway around a circle. In other words, a semicircle. So pi radians turns out to be 180 degrees, which makes sense because 2 pi radians is 360 degrees. Okay, and then pi over 4, well, I can think of this as being 1/8, so pi over 4 over 2 pi would be equal to 1/8 of a full revolution. Or I can think of it as pi over 4 over pi would be equal to 1/4 of a half revolution. So I just consider this half revolution, and I do 1/4 of that. Well, I know that 1/2 of that would look like a right angle, so I know 1/4 of that is going to look like my 45 degrees. Okay. And we can also do something like negative pi over 3. Okay, negative radians are no problem. Okay, we just got to think negative pi over 3 over 2 pi. Well, that would be negative 1/6 of a full revolution. So if I was going to draw it, it would look like, well, we'd start here, and remember, if we're doing a negative angle, we should move clockwise. So I'm going to draw an angle which goes down in this direction, and it should be about 1/6 of a full revolution. So a little bit less than a quarter. Oops. Pi over 3 should be pi over 1/6 of a revolution. Yeah, a little bit less than a quarter, but more than an eighth. Okay, so something around here. All right, sweet. That was rad. So here's some bicycle people doing something rad. Okay, so here's some common angles. Why don't we put the angles together? Angles. All right, in radians and degrees. So common ones that we see are gonna be 90 degrees is pi over 2, 180 degrees is pi, 360 degrees is 2 pi. Okay, and the rest of them we can just kind of get from there. Okay, if we take 45 degrees is half of 90 degrees, so pi over 4 is going to be the radians, which is going to be half of pi over 2. Okay, so all of these things are proportional. Likewise, we can get 60 degrees, that's pi over 3. Okay, and 30 degrees is going to be pi over 6. And so here's how you can kind of convert between all of these. Okay. So now let's talk about how we are going to express a certain measurement of an angle, which is given to us in one form, and we want to convert into the other form. So this is like back in the day in grade school or in middle school or whatever, you probably learned, you know, you had a math problem that said, okay, if you have 20 meters, how long is that in feet? Something like that. Or if you have 100 degrees Celsius, what is that in Fahrenheit, right? So same deal here, we're just going to switch between forms. And the way we switch between forms is by manipulating the equation which we have, which equates an amount of radians to an amount of degrees. And that equation is 2 pi radians is equal to 360 degrees. And what I'm going to do is I'm going to manipulate this equation until I have 20 degrees on the right-hand side, and then whatever's on the left-hand side will be what I get in radians. So if I want to have 20 degrees on the right-hand side, I should divide by 18. Likewise, on this side, I should divide by 18. And so I get 20 degrees on this side. And on the left-hand side, I get pi over 9 rad. So that's my answer, is pi over 9 radians is going to be equal to 20 degrees. Okay, and it's not so hard to go the other direction either if we start with negative pi radians. So we just write down our equation, 2 pi rad equals 360 degrees. And we're just going to manipulate these equations until I get negative pi rad on the left-hand side, and then I'll just check what's on the right-hand side. So I should divide by negative 1. And what do I... No, I'm sorry, I should divide by negative 2 here. And on this side I will get just pi radians, or pi rad. And on the right-hand side I will also divide by negative 2, and I get negative 180 degrees. So negative pi radians is actually negative 180 degrees. Okay, so let's do one more that's kind of hard. Let's try to express 19 degrees in radians. So if I start with my equation here, 2 pi rad is equal to 360 degrees, then here's the issue with doing one that's kind of like this, where we get this 19 here is kind of an annoying number because it's not immediately apparent what should I divide on both sides in order to get 19 degrees on the right-hand side. So I'm going to do the following. I'm going to solve this. I want to multiply both sides by some number x. And I want that to be equal to 360 degrees times x. And whatever I multiply, I want this to be equal to 19 degrees. And then if I go all the way to the left and figure out what this thing on the left is, then I'll have what it is in radians. So I just need to figure out what should this number x be first. And I'm going to do that just by focusing on the right equation first. So 360 degrees times x should be equal to 19 degrees. So what should x be? Well, x should be equal to 19 degrees over 360 degrees. So we cancel the degrees, so we get x should be the number 19 divided by 360. So if we multiply both sides by this, see what we get. We would get 19 degrees. If we do 360 degrees times x, would be 360 degrees times 19 over 360. And that's going to be equal to 2 pi radians times 19 over 360. And now we can cancel the 360 here. On the right-hand side, we get 19 degrees. And on the left-hand side, we're going to get 38 pi over 360, or 19 pi over 180 rad equals 19 degrees. Okay, so that's how we can manipulate this equation to switch between these two forms. Okay, and so my recommendation to you would be to memorize the fact that 2 pi radians is 360 degrees. And to memorize that, you probably only really need to memorize the fact that 2 pi radians is a full revolution, because you already know that 360 degrees turns you all the way around, or at least I expect probably a lot of you guys know that already. So if you do know that, you can just memorize the fact that 2 pi radians makes one full circle, and then just set that equal to one full circle in degrees and manipulate that equation to get what you want in order to manipulate these, or in order to convert radians into degrees or vice versa. Okay, so that's what I recommend. But if you want the cheat code, here's the cheat code. If you want to translate between degrees and radians, so you want to transfer something from degrees into radians, we just multiply the number of degrees by pi divided by 180. So if we have 19 degrees, and we want to express that in radians, we just take 19 times pi divided by 180, and that's our rad. Or if we have pi over 4 radians, and we want to go to degrees, well, we do the opposite of that practice. We multiply, instead of multiplying by pi over 180, we multiply by 180 over pi. So we would do pi over 4 times 180 over pi degrees, and that would be equal to like 180 divided by 4 degrees, and that would be equal to 45 degrees. So this is how we can use the cheat code for going between these two things. So if you want, put this on a flashcard and keep it under your pillow when you sleep at night and try to absorb it into your soul and memorize it. Or you can just remember that 2 pi radians is a full circle, and then you can work everything out from there. Okay, so that's how we convert between radians and degrees. There's one common mistake that I want to highlight. Okay, it is true that pi radians is equal to 180 degrees. However, pi itself is not equal to 180, i.e., 2 pi over 180 radians is not equal to 2 radians. Okay? Because pi here itself, we need to remember, is just a number. Okay? Pi is not equal to 180 unless we specify that we're talking about pi radians being equal to 180 degrees. Okay? Pi itself is actually a number. It's the number 3.1415926 ... and a bunch of other digits. I think we know like 1 trillion digits of pi. No, we know like 30 trillion digits of pi, or something like that. Anyways, the point here is that if we want to set pi equal to 180, we have to be specifying that we're talking about pi radians is equal to 180 degrees. Okay? And the reason that this equation is true is because a radian is not the same as a degree. Okay? That's really the crux of the biscuit, as it were. Okay, so that's a common mistake to avoid. So we're going to do this example, and this will be, I think, the last thing we do. Okay, so this problem tasks us to find 2 distinct angles, alpha and beta, okay, which are coterminal to theta equals 80 degrees and different from theta. So the first thing I'm going to do is I'm going to say, hold up, let's just draw first. What does 80 degrees look like? Well, it's going to look sort of like a right angle, like a 90-degree angle, except it'll be a little bit less, right? It will be a little bit less than a 90-degree angle. So I'm just going to draw something that looks kind of like 80 degrees. It's probably not exactly right, but it'll work well enough. Okay, so here's 80 degrees, and this is equal to this is theta, okay? And I want to find two angles alpha, which is not the same as theta, but coterminal. Alpha and theta are coterminal. Okay, so I want them to both start on this initial side, and I want them to both end on this terminal side. Okay, but I don't want alpha to be just the same exact angle, because that's boring. I want to choose a different angle, but they should be coterminal. So one way I can do that is the following. Rather than just going 80 degrees and getting to my terminal side, I'm going to do something kind of wonky. I'm going to start on the same place, okay? Start on the same initial side, and I'm going to go all the way around and do a full 360, and then some. Okay? I'd go 360 degrees, so I'm back on my initial side, and then I go an additional 80 degrees. So this is the angle alpha is equal to 360 degrees plus 80 degrees, which is going to be 440 degrees, I think. 440 degrees. Okay, so in this case I can go all the way around and then some. And this is a different angle, right? We would say that 440 degrees is not equal to 80 degrees, but they are coterminal. Okay, because they end on the same side. Okay. So that's one way I could do it. Or I could also be clever, and since we're supposed to find two, we might as well call this one beta. We could also, instead of going in a positive direction, we could do a negative angle, which starts at the same place and ends at the same place, such as this angle, beta. Okay, and if we want to know how far we should go in the negative direction, well, negative 360 would take us all the way back around to where we started. So we want to do that, except we don't want to do the final 80 degrees, which would take us all the way to 360. So beta is actually going to be equal to a 360 degrees minus 80 degrees. And that would be 280 degrees. So again, we would get beta equals negative 280 degrees. Negative 280 is not the same as 80, but these angles are coterminal. Okay, these angles are coterminal. In fact, if theta is an angle, then theta, no, not theta, why don't we call it alpha n is equal to theta plus 360 degrees times n, where n is any positive or negative integer that is, n is going to be something like 1, 2, 3, 4, dot, 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 or negative numbers with whole negative 2, negative 3, and negative 4, dot, dot, dot. Okay, so n is any positive or negative integer, and we take theta and we add 360 degrees times some integer, well, it's going to be coterminal. If alpha n is defined in this way, we have alpha n and theta are coterminal. So, for example, if theta equals 30 degrees, then alpha 1 would be 390 degrees. Alpha 2 would be that plus 360 degrees. Geez, what would that be? So 300 would be 690 plus 60 would be 750 degrees. And then like alpha negative 1 would be equal to negative 330 degrees. And alpha negative 2 would be that minus an additional 360 would be negative 690 degrees, and so on and so forth. All of these numbers, all of these angles, all coterminal. Okay, you can see why, because if we start with an angle of 30 degrees, okay, here's 30. If we do 390, that's this many. If we do 750, then what's that? That's going around once, and then twice, and then an additional 30 degrees, right? This is 750. You can see what we're doing here. We're just spinning around multiple times and then getting to the same spot. Okay? And what these negative ones tell us is we can also go around in the other direction. We could do alpha negative 1, do negative 330 degrees in this direction, or negative 690 degrees would be 2 circles in this direction. Oops. This should have gone like that. And then the other one would go all the way around and then some. Okay, so this drawing looks hideous at this point, but the point is we can spin around as many times as we want, as long as the final revolution, the final spin, we only go that one little amount to make our angles coterminal. Okay, so I think that's where we stopped with the class today. So I got through this pretty quick. No pauses for classroom interaction or for questions. So what I'll say is, if you have questions over this material, please bring them to class tomorrow or bring them to office hours on Wednesday. If this stuff was a little bit too fast, since you didn't really have the opportunity to stop me, although I guess the people on the YouTube channel don't ever have the opportunity to stop me, so I suppose that goes for all time. All right, well, that's it for today. Have a good day, and I'll see you guys next time.